So specifically a runtime for WebAssembly. So WebAssembly has gained traction both inside and outside the browser as a way to sandbox untrusted code. For example, CDNs like Fastly and Cloudflare use WebAssembly on their edge cloud to isolate tenants from one another, preventing them from reading each other's sensitive data. Similarly, Mozilla uses WebAssembly to sandbox third-party C libraries in the Firefox browser. Now, the reason that these companies are interested in WebAssembly is one key property, that the WebAssembly compiler instruments untrusted code to restrict it to its sandbox region, which suggests that as long as we get the compiler right, that WebAssembly is totally safe. But this is only really true when the untrusted code is executing strictly within the WebAssembly sandbox. And it turns out that this is actually often not the case. This is because most sandbox code needs access to resources outside of its sandbox, like the file system. In WebAssembly, this is provided by WASI, the WebAssembly System Interface. WASI provides a low-level, OS-agnostic API for using OS resources. The calls to this API are known as host calls, and they play a very similar role to system calls in an operating system. Let me just give you a quick sketch of how this would work if a sandbox, for example, wanted to read from a file. First, the sandbox invokes the WASI read host call. Then, the runtime checks that each parameter of the host call is safe. Here, it would check that the WebAssembly pointer actually points to within the sandbox's memory. The host call is then translated from the OS-agnostic WASI API to a specific operating system implementation. Overall, the implementation of the host call has two responsibilities. First, it must bridge the API difference between WebAssembly and the underlying operating system. But just as important, it must maintain isolation while doing so. And if it doesn't maintain isolation, this can lead to sandbox escape, which does actually happen in practice. In WebAssembly runtimes, in other sandboxing runtimes like Google's NACL, and in all sorts of academic systems. And it's not because the WASM or Google developers are sloppy. They're quite skilled and they have very good security practices. But it's simply unrealistic to expect developers to put all the right safety checks in all the right places every single time. So what we'd really like is a way to describe the runtime safety policy and use an automated tool to make sure that this policy is preserved everywhere in the runtime code. And turns out this is a really great use case for automated verification. And so for the rest of this talk, I will tell you about how we went about building WaVe, a verifiably secure sandboxing runtime. First, I'll give you some intuition as to why it's so hard to secure these runtimes. Then I'll talk a bit about the design and verification of WaVe, our verifiably secure runtime. And finally, I'll discuss our effort at empirically evaluating WaVe's correctness and performance. But first we have to ask, what does it actually mean for a runtime to be secure? Well, some safety properties of a runtime are obvious. For example, the runtime obviously needs to preserve memory isolation. In short, all memory reads and writes performed on behalf of a sandbox should target memory that that sandbox owns. The sandbox should not be able to cause a read or write to another sandbox's memory or to the runtime's memory. A less intuitive property that WASI runtimes are expected to uphold is file system isolation. Every file that a sandbox can access needs to be within the sandbox's root directory, similar to the policy used by, say, BSD jails. For example, for a sandbox rooted at foobar, if it wants to open /data.txt, great, that's fine. Similarly, /baz/picture, awesome. But it tries to exit out of its root directory and read secret.txt, the runtime needs to deny that. And then our final safety property is network isolation. Sandboxes should only be able to create sockets to a known and explicitly allowed protocol, and only to addresses specified in a deny by default access control list. Furthermore, the sandbox should obviously not be able to modify its own access control list. Now, these properties are fairly straightforward, so why are they so hard to get right in practice? Well, it turns out there's a couple of different reasons. The first is that OS semantics are complex and informally specified. For example, here's just a small fraction of the specification for path resolution in Linux, specifically coming from the man page. Path resolution is the process by which the OS turns a string representing a location in the file system into an actual handle into that file system. And this process can be very complex, handling every possible combination of path resolution flags, handling recursive symbolic link resolution, and other challenges make it very error-prone. And all the developer has to assist them in this effort is a sometimes ambiguous English-level specification. So you may say, sure, POSIX could be a little bit of a mess, but surely WASI, coming from the world of WebAssembly, where they highly value formal specification, may be a bit better. Unfortunately, you would be wrong. So here's the specification for FD-read in WASI. It reads, read from a file descriptor. Note, this is similar to readv in POSIX. It doesn't really say what the host call is doing, and it certainly doesn't describe the safety checks that you need to perform in order to make sure that the host call is safe. And finally, as I've alluded to, we are relying on developers to simply get all the right checks right every single time, which means in practice, assumptions about OS behavior and host call behavior are left implicit and scattered around the runtime code. So in the rest of this talk, I'm going to tell you how we overcome these challenges in WaVe. WaVe is a WebAssembly runtime. It implements WASI using the standard check and translate process I outlined earlier. But what isn't standard about WaVe is that it actually verifies the correctness of this process. WaVe does this using an automated verifier, an OS specification describing operating system behavior, and a safety specification, and verifies that the runtime code preserves WASI's safety guarantees, thereby removing the runtime from the trusted computing base while only relying on two concise specifications. And it's really the design of these specifications that help us overcome the challenges I just outlined. The first of which being that the OS semantics can be complex and informally specified. Well, what do we want out of a specification? Well, ideally, we'd like it to be simple, and we'd like it to be formal. Unfortunately, existing formal specifications are very complex. Don't try to read this, but this is just a very small part of the specification for the read system call in CivilFS, a system for finding bugs in POSIX implementations. Since it's meant to find subtle implementation bugs, it models all the gnarly details of file system internals, which is awesome for their use case, as they can use it to find some really cool bugs, but it's not quite appropriate for WaVe. All we really care about is that read writes to a portion of user space memory, which means we can largely ignore the internal details of system calls. For example, this is the specification for the read system call in WaVe. All it says is that we write to buff for up to count bytes. And it turns out that all these syscalls that we care about can be modeled in a similar way with a small number of effects, which means that our total set of effects can fit on this one slide. There are 2 effects to model reads and writes to user space memory, 2 effects for modeling accessing files, and 3 to model accessing the network. But of course, we have to ask, how do these actually help us to build a secure runtime? And as it turns out, the effects will help us specify what security really means in WASI. For example, we can now make the safety conditions for a host call like FD-read explicit. In particular, we can write an ensure clause that says that the host call FD-read should only be allowed to write to the part of the address space that belongs to the sandbox. The verifier then ensures that when we perform the POSIX read, which can write to arbitrary parts of memory, that we only do so with arguments that are checked properly. In practice, we don't actually write the WASI specification this way. We could, but writing a specification for each host call would be a pain. It's also not necessary, because our safety constraints are not really per host call, but per effect. And since our OS specification describes system calls in terms of effects, we can centralize all our safety conditions into one single policy file that applies to all host calls. Let me walk you through a bit of this spec now. At the top level, we have a clause that simply states that we're going to enforce an invariant over all possible effects that a sandbox could cause. So if the verifier wanted to prove that all reads performed on behalf of a sandbox were safe, It would see that the read causes a memwrite effect, and then enforce that the buffer being written to is within the sandbox's bounds, and that we do not have an integer overflow. And these very same constraints would apply to any system call that causes a memwrite effect. The end result being that our spec is both centralized and very concise. In total, it's only about 45 lines for the safety spec. Now, our verifier uses these specifications to prove the safety of the runtime code, but a natural question to ask is, how do we actually know that we got our specifications correct? Well, we first have to think about all the places that bugs could still pop up in this system. In the OS spec, we could mischaracterize the effects of a system call. Our safety policy may not reflect that of actual runtimes, and our verifier could have bugs. To test the OS spec, we use a custom OS fuzzer that measures the effects of system calls on user space. To test that the safety property reflects that of actual runtimes, we differentially fuzz WaVe against other runtimes. And while this wasn't our work, another group actually completely re-verified WaVe using a different verification engine based on refinement types in Rust, reducing our trust in the verifier. I don't have time to go into detail on all of these, but you can check out the paper for more. And finally, we wanted to measure how WaVe's performance stacks up against industrial WASM runtimes. So we measured it against the fastest popular runtime, WASM time. We did this on 3 sets of benchmarks, 1 set of micro benchmarks, and 2 sets of end-to-end applications. In all end-to-end applications, WaVe outperformed WASM time, showing that we don't have some huge performance overhead for using a verified runtime. In summary, WaVe is a verified WASM runtime. Thank you. I can take questions.
Thanks for the talk. So I had a question about the constraints you have on some of these functions. So in the POSIX example, the reason why it was so complicated is because they presumably have to do stuff about, well, if you're a user, you might not have permissions for this, or if it's mounted on a particular block device that has certain flags set, you might not be able to touch this. This version of ability to read seems very coarse. For example, you might have this function that is fd write, but if the user doesn't have permissions, it would still go through, right? Because the only thing the effect says is, well, you're allowed to write to this pointer, and makes no claim about the permissions, right? So did you find that there was a mismatch between more complex permission systems and the effect system that you wrote?
So the effect system that we wrote was really kind of focused around enforcing these sandboxing rules on top of POSIX. So for the most part, what that ended up being is that, for example, for the file system stuff, that we're constrained to this root directory. So we're less concerned with per user permissions, I guess, as all of these sandboxes are going to be running in a single process under a single user's permissions. A lot of the complexity from the file system stuff comes from how weird it is to do recursive symbolic link resolution and stuff, and just making sure that you actually end up within that root directory. We're less concerned with permissions type stuff, I guess.
Okay, so that's why you can make it all just as simple as possible in the effect system.
Yeah, we cut out a lot of the stuff that's not kind of focused to the sandboxing rules, I guess.
Okay, thank you.
Next question, please.
Hey, Atribhar Acharya from EPFL. So I have a question about how confident you are that the behavior which you extracted from the operating system using a custom fuzzer actually correctly models the behavior of the operating system as per implemented. Now, just to give you a reason why I'm asking this, is just that Linux follows a very interesting policy that there is no bugs, only features, especially if users depend on it, and that the source code is the ultimate documentation. So are you sure you can capture the finer weird behaviors that Linux or similar operating systems have?
Yeah, so there's kind of 2 parts to that. The first is that, yes, we used our custom OS fuzzer to try and measure what the effects on user space are. Obviously, you're never going to get 100% fuzzer coverage through a system call in Linux. or it's very, very difficult. But for the most part, the behavior that we care about is stuff that would kind of that would directly affect our sandboxing rules, like things that could break our user space sandboxing rules. So if there are like funny little nuances in what result code a system call returns, I guess we don't really care about that sort of stuff.
Yep, okay.
There's also the point that like there are some system calls that are like just kind of too complex to really model. Things like, I don't know. ioctl, exactly. But luckily, the people that design sandboxing runtimes, I guess, know enough not to even let people use it. So it also really helps that we're working on some kind of like a somewhat constrained set. I want to say there's like between like 40 and 60 system calls used. It's a fairly constrained set that is like mostly pretty reasonable, although there's a couple of complex ones in there.
Okay, thanks.
Cool.
Okay, maybe one quick question.
One quick question. Nathan Downhan, Rice. eBPF, all this nice promise. How is this different?
How is like WebAssembly different than?
No, not WebAssembly.
Okay.
The proof methodology, right? So eBPF is a flippin' mess. But right, they have a runtime verifier, checker, and all these getters and setters. And I'm just wondering, what about your method? Do you deal with similar types of attacks, or can you verify your runtime, or these types of things? Have you thought about like the verifier bug? I mean, obviously you showed some things.
Yeah. So I guess there's two parts to the eBPF. There's the part where it's like actually executing and making sure that the thing running is memory safe. And that's something that's not really handled by WaVe, but would be handled by like a WebAssembly compiler or whatever. As for like handling system calls, let's see. So one thing you could do is you could build like a verified eBPF, like verify the equivalent portion of the eBPF runtime that we do for WaVe here. But like, for eBPF, the bits that are actually like handling all the system calls and interacting with the outside world, you could use the same methodology for that.
Thank you.
Cool.
Right, let's thank our speaker.